We'll have a small recapitulation of this topic from last week, and then we will also pick up the exercise. So what are the results there, and discuss it with you. Okay, so last week you had a look at academia, and so my personal impression is that it's very similar to pastry. So if you have a look, it has it uses an ixometric to compare the difference and the distance between the nodes. So in this case, if you have two numbers given, then you create a XOR and it tells you how far they are apart. If you think about it, then it's also very similar what prefix matching does. So how far is the distance? The distance is as far as the first bit is different. And this is also the same like in a prefix. So it checks which is the common part and then where's the first difference. And later on, you can still differentiate between closer or further ones, but it also detects the first different bit. Okay, and then it offers you two options to either find a node or to find a value, which is managed by a node responsible for this value, for this key. So, and also here, you do as in pastry, you have your routing table with distances in exponential distance. So for every possible bit in the XOR, you have a bucket. So how far the nodes might be away. So if the first bit is different, you have a bucket. If the second bit is the first one that's different, then you have a bucket. For the third bit, you have a bucket. And the difference to pastry, so pastry would have in this case, so this would be the case when we have pastry with only two characters, so b equals 1. But here we have the option that for every distance we can have, so we have a bucket. That means multiple entries that are possible. And typically, so Academia has the parameter k for this, and one typical value that is used nowadays is 20, to have 20 contacts for each distance, for each node that is so far away. And this is a little bit complicated to explain, but I would say this is the first bit in the 160 bits. If you compare them, that is different. So therefore you have the buckets. And what you do, then there's a policy on how to include the new nodes into the bucket. So if you learn about them, so you don't have to actively search for them, so you just have a look at the messages passing by, and then you see, okay, do I know this node? Is he valuable to put in my routing table or not? And then you, if there's space in your routing table, you put him inside. If there's no space, then you drop him, or you check at least whether the full bucket has one offline node, and then you check the last one in this bucket, the last seen online node, to put him inside. So you have the different 160 buckets which is the pendant or the same like having the shared prefix with the various entries, and you have also waiting list, and it's quite working very robustly. How's routing done? So this is something new. So what it does is it has this iterative and parallel routing. So parallel, that means you send out two or alpha many requests, and every of these node participates then in the routing. And the routing is not like in core that every node passes on the message to the node that he finds suiting best, but they tell you back which would be the k closest nodes they know, so that you have to send out the next request. Why is this good? So on the one side, you learn more about the network, what kind of nodes they are. Then you can put them into your routing table. Also, you can decide out of these alpha many replies, and each of them tells you k new nodes. So that's alpha times k. That's quite a lot of nodes. Which are the best nodes I could contact next? So you pick. So in this case, alpha is 2 and k is 2, and then you get 4 new nodes that you learn about, and then out of these you pick again alpha many nodes. And if you take normal numbers, so from real applications, they typically have alpha equals 3 and k equals 20, then you get 60 nodes that you can choose from. And if one node fails or one node is low, then that doesn't matter, because you have still alpha minus 1, so 2 other options that reply quickly and provide you also good results. So this is something very nice. And then you find the k closest nodes. This is a little bit different to pastry and to chord, because here we don't have this leaf set. We don't have the successors and predecessors in Kademlia. This is something very important. So every of these nodes, which are closest to this searched key, they don't know whether they are the closest. They just know they don't know anyone else closer. So they don't try to find closer nodes. So on the worst case, you have the case that if you start several lookups for the same key from different positions in the network, you get different, mostly overlapping, but somehow different k closest nodes. Yes, so this were the nice things: parallel queries, iterative queries. The network maintenance is done passively, so by learning about the network, and we have large routing tables, so we have these buckets which give us more freedom. So for every distance we have 20 or k contacts that we can choose from based on any kind of metric. Okay, and that was the problem that I just mentioned. So it might be so that there are some investigations and some papers that analyzed that if you state really the same lookup for the same key from different positions in the network, so this might be the first set of nodes, so k many, so in this case k is 4, and later on somebody else is doing a lookup, so 2 nodes out of these 4 are matching. Okay, that's good. They consider themselves as closest. That's good. And now somebody else tries to update. They also have a match, but they are not matching the initial published. So Kademlia is not suitable for updating data. So if you want to change your data later on, you don't have the guarantee that you reach really all of the nodes you stored it initially. And if you miss one of these entries, and obviously you don't miss one, but you miss 82%, then you have the problem that they are still in the network. So you don't know if somebody is making a lookup later on, and you updated only 18% or different 18% or whatever you updated, but they reach a set of nodes which give them different answers. So you ask for a key, and please return me the value, and you get different versions of this value, different versions of this data. You don't know which one is the newest, which one is older, so you don't have this consistency on the network. In chord and in pastry, it is given. So every time you do a lookup, you then overlays make sure that you really arrive at the one single responsible node. And this is quite useful if you really want to build more complex applications with it, where you also want to change data. So how Kademlia is used, it's not really needed because it's for file sharing. So you upload your announcement that you have this file, and people can download it from you, and it's only it's valid for 24 hours, and later on it's gone if you don't refresh it. But it's not meant to be updated. Okay, then there was this example of the real application. The hypercube networks, that's I wanted to also pick up CAN, so that's I was asked to repeat a little bit in detail, especially the departure part. Okay, so let's go also through that. So we also had CAN last week, and CAN makes something very different. Or first, do you have some questions to Kademlia in this repetition? Okay, so with CAN, what is interesting, what is new, is that we have this two-dimensional, not just two-dimensional, but n-dimensional or d-dimensional space. So we have d axis, dimensions, and the nodes allocate positions in these networks. How do I say it? So the network and the topology grows with the number of nodes. So what is special is that we have always this kind of tree structure. If we look at it from a top or from any kind of dimension. So in 2 dimensions it's easier to see, or also with 1 dimension. With 3 dimensions also doable, but it's this way it's quite easier. So what is special is that the nodes don't have random positions in the network. So they don't hash their value and then it's now, I would say, I don't know, in this spot up here. No, they have to select dedicated points in this kind of topology. So when a new node joins, then he might compute his position, like let's say it's up, yes, it's somewhere down here, I don't know, so 1 and 1. And now we find the node who is responsible for this spot, we contact him, and then he splits up his zone. Oh, and this, okay, it was this case. So we find a position, this is a new node, and we find a responsible peer for this. We contact him, and we don't get the position up here, which we calculated up front, but we get this dedicated position in the tree. So it's, the nodes can only be placed at this special points in the network. Okay, and once this is done, so they have their neighborhoods, so they can only connect to their neighbors that are where they have a common border, and this is how the network grows. So every time a new node comes in, it finds its position in the responsible peer for its position in the network, and then, as you can see, the N2 that was previously responsible for this whole area shifts its position to a new dedicated spot in CAN. So this is something special. So they change their positions also in the network topology based on their neighborhoods. So this was not the case in Pastry and Kademlia and Cord, where they really had from the beginning on one fixed PID and that didn't change, and their position didn't change. Okay, so this was something special. And then if you do the routing, then you just go through your neighboring nodes, you calculate based on this d-dimensional space, you calculate the shortest path, and then in that direction you can go. And there are also simple rules how you can go. So in this case, for example, N5 didn't contact N4 before, because you can calculate the direct line to the destination node and check which borders are crossed, and that borders you have also to cross with your routing. So there are some simple rules. What is interesting here with the routing, that we don't have O log n routing, but d square of n, so d times d square of n. And why is this? So one moment, because so what is the routing complexity of CAN? So if we have a look at the simple 2-dimensional case, then we have, so this is, let's say if we wouldn't go around, this is just a factor, this is the longest possible path that we can go. And if we do not consider that it's wrapping around. So if it's wrapping around, then it's just a half, but just for simplification. And then what do we have here? So how long is this path? And this path is, so if this is the question, how many nodes do we have to cross in this direction? How many nodes do we have to cross in this direction? And the overall distance as you have is, you have to cross, so this is the square root of, so this is this one. I hope this can be read. I think it's also, let me just find the slide. Yes, okay. So that's what we want to go to. So why is it d times that one? This is because so we have to first go once across this part and once across that part. Or better, I think it was even in one exercise, and I would like to ask you for that. But so if you it's a little bit difficult to explain multidimensional, but I will come to this one in yeah, in one exercise I would give you, and then it's easier to explain than in this wrap up. Okay, but what is more important now in this can is what happens if a node fails, when a node goes offline. And there are two options. So if we consider this tree structure, so you always have to keep in mind that we have this tree structure like down here in mind, and this tree structure is easier to construct if you have a clear rule. So for example, that you first split vertically, so that you first have this n1 over n3, or under n3, and on the other side you have, on the downside you have n2, and on the upside you have n4 and n5. So first you split this way, then you split this way, then you split this way, then you split this way, so that you have the clear rule. And then it's the question, if one node fails in this network. So let's say we have this example, and n4 leaves the network. Then we have two cases what can happen. So first of all, how is it detected? So first of all, it's detected by the neighbors that check periodically, is the node online or not. And in this case, one of the neighbors detected it. And who should now take over the zone? The zone is taken over by the one that is first getting active, and based on the size of the network. So ideally, a small node, a small zone, should more probably take over the remaining part. So this is now abandoned point and fourth place, and now either N2 or N5 should take over in the initial step, so they should get active. And 2 points might happen. So in this case, N6, for example, got lost. And if we create the tree structure for this, so again we split first according to this. So then we have, and then according to this. So this is N1 and N3. And here again we split like this. So then we had here N2 and 6, and we had yes, N4, I think. Was it N4 or N5? Doesn't matter. So okay, and now we find out N4 is gone. So what should happen? So the easiest case is that not. So this is not the easier case. So the easier case, if let's say if one of these inner nodes would fail, so where you have a direct neighbor on the same level of the tree. So if I would just create the drawing for it, one moment, then it's a little bit more clear. So if you have an inner tree which is, so this is a small part of the network, and based on the whole tree, so you have here the can, and so A and B, and if A is missing and A is on the same level of the tree, the neighbor of B, this is the simple case, and then if A is lost, then directly B should move up and take over the whole zone. So this is a simple case. So there you just check, okay, my neighbor on the same level in the tree is lost, and now I'm the responsible one and I take over the whole zone. This is the simpler case. The more difficult case we have if we lose a part, if we lose a zone where, like in this case, where N4 was lost. So in this case N4 was lost, which does not have one single node on the other side of the tree, but 2 or more. So it can be also a tree down here. So what is there the rule? The rule then is that if this node is lost, then out of this other subtree on the other side, we go very down, 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 until we find a leaf which has something like, which is in the easier case, where 2 nodes are opposing on the same level, and one can take over the failed node on the upper side. we can also go through this in the exercise. That's probably a good point to discuss. So what you have to do is, if some node is failing where on the other side of the tree more or multiple nodes are, you have a subtree, then you have to go down in the subtree until the very bottom, until you find 2 neighboring zones on the same level, and then you pick one as a new responsible node. Maybe this is also the point where we could discuss the exercise, so especially about can, and then also go through code and then pick up the new topic. So we had this, I think, already a solution exactly. So the first question was with the diameter, but I would like to jump to the defragmentation. So we had a CAN network given. One moment. Yes. This one is the CAN network. I just take this one. Okay, so you had to draw CAN network with the situation before and leaving after the before and after leaving the zone. So where the complex case is and where the simple case is happening. Do you have such an example? So for the simple case, I think it's easy. Then probably, we have it already discussed, but for the complex case, it would be better to have a longer case than just that one that I sketched on the table. Do you have some suggestion for a simple case, for the just your own CAN network? So these are typical questions in the exam, so please draw a simple CAN network and then we see how it, so what happens if a node leaves the network. So okay, let's again discuss this. So let's take this network, I don't know, A, B, C, D. So how would you draw that as a graph, or is it as a tree? How many branches so does a tree have? Yes. So if we split, so we have to make some rule how we split. Let's say we split first this way and then the other way. So then it would be A. Yes. Oh, let's make it this way. Okay. Okay. And now if C is failing, then yes. So if C is failing, then we see, okay, this is lost, and B finds it out because they are neighbors. Also D and A will find out, but they will have timeouts, and B is reacting first, and B sees, okay, I'm the responsible one, and it's on my level, so I will take over, and then this will be gone, and B is then responsible for the whole part of the network. Okay, this is the simple case. Now the complex case, again with A. So B, C, let's make it D, D, E, F, G, H, I, J, K, L, M, N, O. Okay, and now you guess which node is failing. So let's, how would this tree look like? So again, if we start with this, what would be on the left? Yes, A. No, again, only two. Only two. Yes, only two. Ah, okay. One moment. Now let's, so let me just, one moment. This is everything starting with B, everything starting with J. Then we have here everything again starting with B and everything starting with C. Let's go through. Then everything. Okay, this is now. So then here it would be B. One moment. And this is. So this is D, F, E, G. Yeah, because this is this split. Then one above. Yes, that's, sorry. It's only that one. Then this is the bigger one. This one. This is then again this one. And so on. Yes, so the first split is all everything with A, and this is everything with B. And then here we split again the B branch. So this is now the split. Yeah, B and C and D and E and F and so on. So all this upper part. And this is the lower part. So for the lower part, here we could, for example, make. Sorry? Yes, so all the lower part. One moment, I just make it a little bit now like this. And it's now everything with J and everything with M. With M it's easier. M, O. And this is the N. And this is J, K, and this is L. Okay, very long. And now A is failing. So A is always, so now this node is failing. So which nodes will detect it and will take over? This is some complex case. So what happens? All of the neighbors of A have timeouts based on their size. So the smaller neighbors, and the smallest are D, F, J, K. And don't forget, these on the other side, so if I would be a little bit smaller, so they are also neighbors to A. Okay, so let's say, I don't know, J or K detects, or doesn't matter which node detects, even if it's N. So let's say, I don't want to take a too easy one. So let's say N would detect it just by random. Then N would be for a short time responsible for this part as well. So yes, probabilistically the smaller ones will detect it earlier, but let's say N would detect it for a short time. Now N is also responsible for this part, so for A's part, and we have this case. That N is responsible for this L-shaped zone. It's not ideal, but it's okay. Okay. So N is now responsible for this part. Whoops. And this is now the zone of N. So N is also here and N is also there. So now N starts the defragmentation period, yes? Why did you choose N? Because it's probabilistic. So if I would, typically the probability for the smaller ones is bigger, but then the example is too easy, because then they are already good enough to take over the zone. So typically they would have the bigger probability to take over, but the example is nicer to understand if somebody else takes over. You can also play it through with the other ones. You can also play it first through with K, for example. If K takes over, what would then happen? Yes, so if, okay, let's play it through this case. One moment, I have to. Okay, so let's say not n is taking over, but j. So this one, then it's easy. J checks, okay, on my local area, so where I'm also responsible for, there's on the same level of the tree, there's one single node. So K could take over my part, like this. K, and J is the new responsible one up here, and everything is fine. Yes? That's easy, because here he could give up his old zone, so he doesn't have to keep it. He took over the one, and that's good. That's too easy. So that's typically most of the times happening, but for the exercise, let's try something else. So if not J is randomly picked out but N. And N is a little bit more complex because N cannot take over the zone of J, so he has also a subtree where he is responsible for. Yes, and what happens then is that N checks in his neighboring subtree. It goes down until he finds a leaf which has on the other side, so where he finds two leaves on the same level of the tree. So again we are at J and or K, and let's say he selects in this case K. So he tells, okay, K, please take over this role, and K takes over, and J takes then over the area of K. So N, it really remains at this point, but he asks one leaf on the other subtree to take over the zone of A. So you always have to go down to the leaves before you can assign a new responsible node for the left node. Yeah, so first you take over, and then you keep it until you find a good replacement. And you find a good replacement, and by going to your neighboring subtree, go down until you find two leaves on the same tree branch, and then you pick one of them, and the other one takes over the zone. Yeah, but N has a subtree. No, but the nodes are always leaves. Yeah, but yes, no, I ist HI, wo ist denn HC? Hä? B? C? Ah, no, here we made a small mistake, so I would not, so it would be like this, so C and HI, something like this. So there's no C. So there are no inner nodes in the tree. So we only have leaves in the tree. If we would take C, who would take C? If C would, then B is here. So let's say if B is selected to take over the zones. Yes. No, I don't get it. So you always no. So up here we don't have we just have, so we only have leaves, and we have to find a node. So we have to find two leaves on the same level, and either if we have it directly, or we don't have it, and then we have to go down on the neighboring path to find it. Okay. And here was also the other question. So this is the solution for this. And here the question is why the routing diameter of can is so you have to find out what the routing diameter of can is in this exercise. Let me just increase it for you. Do you have some suggestion how to show it? Yes, you have to have your neighbor in the tree has to be a leaf so that you can take it over. And if your neighbor is not a tree, is not a leaf, but a subtree, then you have to go in the subtree to find 2 leaves there. Yes. Okay, and then the question in the exercise was also, okay, so this 2.A, so what is the, no, 3. Why is it called 3? It's exercise 2. Okay, so what is the path length in CAN? Any suggestions how we calculate the path length? So the path length was already given. So we had the path length of O of D times N. So this is D. Any ideas how we can show this? Yes. That's true. So I can try to visualize it. So that's true. So on the one side we have, that's it. Big. So I just put it down. I need a better microphone if you can recommend one. So you have this. So the key is that you have n nodes in the network. So let's say these are n nodes in the 2-dimensional space. So we have here. So to make it more clear, 2. So d is equals 2, and in order to get n nodes, so we have here this many nodes, so square root of n and square root of n, and if we multiply it, then we get n nodes. And the same for multiple dimensions. So if you have 3 dimensions, then you have to multiply. So you, as you said, that's true. So we have here always in this axis. So in this part, so if we count them, we have this number of nodes, and also we have in any axis that number of nodes. And if you want to go across, so this is the longest way, then it doesn't matter how we calculate them. You have to cross it once, you have to cross it this time, so d times for every axis that we have to cross it. D times so many nodes you have to cross. So it's the same length whether you go first full to the right and then up, or whether you go across, it's the same. Yes, and that's why it's square d times d square of n. Yes. There was also another question with regard to strange topologies. Let's pick up this exercise. And there was a strange topology like here, so where we have n nodes, and the object IDs are also mapped to the nodes based on k mod n. So every object is assigned to one node. And the question is it, so it's not a good basis for DHT, and why is it not good? Any ideas? Yes? I think so. The first one is, I think, true. So if new nodes come to the network or leave the network, then it will be doable. Then you would have to, then all your mappings would be lost. So you would have to assign new IDs, and that's too costly. Routing could still be possible if you have. I mean, you could still apply some routing approach like in Chord or so. But another point is the limitation of the number of objects that you can have, because typically the overlays are created in a way that they can really carry lots of data. Yes, and that would be limiting. And another point that's also a problem is, how do the nodes know what n is? So how do they know that it's 17 or 17,518 and not one more or one less? So you really have to have the exact number of nodes so that calculated, so that all nodes work with this number and they all produce the same network. And that's very difficult to really have the exact number calculated. We will also learn some approaches how to monitor those, how to calculate these values, but it's not easy. So the network cannot grow or shrink, and it's hard to calculate n. Okay, then how can it be? So we could route different ways. So we have two variants given here for this kind of network. So either we have this, we have the predecessors and successors for every node. And the second one is all nodes are connected to node ID 1. So what is the complexity for the hop count and for the state complexity? So how much storage and knowledge about the network one node has to know? Any simple solutions for that? So what is the routing complexity of the first variant? So how many hops do I need in O calculations? Okay, so let's draw it somewhere. Yes, maybe here. Okay, so the one, so you just have them lined up, just predecessors and successors. How long will it take? So O log n for the hops, and how much storage space, or how is the routing table correlated to n? So in this case, so if this is n, how is the number of contacts you have related to n? Yes. And this is, yes. So this is the state, so the number of so auf Deutsch Zustand. So how much information you have to have about the network. And the other one, so in the other case, all of the nodes are connected to one single node. What is here the routing complexity? Yes, -1. No? No, so how many hops do you need to connect to any other node? So n-1 might be the case for a different question. Yes? Yes. Yes. And for the state, so how large is the routing table in worst case? So is it then exactly? So these are the two observations. So because we have, yeah, as you explained, so in the first case we have, in the worst case, not to traverse n nor hops, but because we could route in both directions, maybe think of something clever, but O of n and O of 1 for the state, and the second one quite the other way around. Okay, what also comes quite often in the exercise, in the exam, is to discuss chord, and given a small network, what is the, so typically I ask what's the responsibility area of the nodes, and to which nodes are these nodes connected. So in this case, for this network, what would be the responsibility area of the nodes? So let's start with the node 1. So where does it start and where does it end? Or let's start with node 8. No. No, you don't have to. Yes, from 88 to 1. So predecessor plus 1 to the current ID. So that's for node 1. Yeah. Exactly. And for node 8. Yeah. Yes, from 2 to 8. Yeah. Again, predecessor plus 1 to the own ID. And for 32. Yes. So 32. Not 31, yes. So what is happening is always the nodes. So you always have to, I think that was question number 2. Yes, exactly. So you always have to, you are always responsible for your own ID and back to the predecessor plus 1. Or to say it otherwise, so if you have this kind of ring, what is also sometimes considered, let me just see whether I can draw something. So if you have one ID somewhere here, it's always the successor node responsible for it. So everywhere in the node, always the successor node is responsible for it. So this is the other way to have a look at it. So anyway, so if you have an ID 40, the successor node of it is 67. So this is the responsibility. Then there was the question, okay, how is it with the fingers and with the node 82? So first of all, how many fingers do we have? And here it was the ID range was between 0 and 99. So how many fingers do we have? Yes. Yes. Yes, that's true. And so what are the fingers of the node 82? So what would be, what are we looking for? Which IDs are we looking for? Yes. And yes. 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 Yes? Mm-hmm. Yes. Mm-hmm. Mm-hmm. Okay. And now the question is, why don't we calculate more fingers? Would it be... Would we gain something with it? If we would have more fingers? So now we have all these fingers. I think I also have the graph for it. No, don't have the graph. But so most of our fingers are pointing. So some of them are pointing to 86. Then we have a few pointing to 1. And we have one pointing to 32 and 67. Okay. So now we could also go further and calculate more fingers. Would we gain some benefit? So it's somewhere here, I think. Yeah.
I don't think so, because you're really fine-grained in your neighborhood, so you can find almost anything in the neighborhood. If you want to find something that's further out of your position, you can just ask your one of your last fingers in their neighborhood, and they'll tell you where to find your desired ID or whatever. And if you just add more fingers, you just worsen your lookup complexity and not really gain anything by it.
Yeah. So yes, so that's true. So we have this property that we are know more about the local area and less about the distant parts, and it's you don't gain too much. And one reason is that what is the goal? The goal is to always halven the distance to the destination node. And with the fingers that we have, especially with the last finger, this is already pointing to the other side of the network. So everything that is further away, we would, with the last finger, already halven the distance to. So we would not gain anything if we would get 3/3 or so, or even more approach to the destination node, because we still have the logarithmic routing. And another point that we have is, so for this fingers that we have up to now, we don't have the turnover. So this would resemble 46, and if you would take 2 to the power of 7, then we would twice apply our mod. So we would go in circles and then come into regions which we already covered with our fingers before. So we don't gain anything. So we covered that regions already. So we covered the whole region with this, and to every point in the network we have a finger which allows us to halven the distance to it. So this is a nice thing. Okay, so that was with regard to the exercise and with regard to the CAN repetition, especially about how the zones are split. So always keep in mind that in CAN our goal is, if somebody detects that the node is missing, and he does so, if he is on his own level, he has some neighboring leaf, then it's good. That's the best case. We can take over, and the neighbor takes over our last position in the tree. And if we don't have one single leaf at the other side, so in this case n, for example, or I can also show it in this. So if we don't have a leaf in the neighboring, like here, for example, n5 is lost, or it's a bad example. So if you don't have some neighboring node in our one single leaf in our neighbor, then we have to go down this neighboring subtree until the bottom, until we find 2 leaves, and one of them can take over. So this is the trick. Okay, so this is for the repetition and the exercise for today. And as a next step today, we start with that we also covered, so the Dupree networks. Yeah, okay. So we today start with geographical overlays. So we have half an hour, and we start with some new kind of functionality. So up to now we always had the function to either have the search for data, where you define your keywords, and then you want to have a set of files offered you. Or we had the option of the DHT, where you said, give me the responsible peer for this object ID, or to route a message to that responsible peer. So it was about responsible peers. And now we introduce location awareness. And what is location? What's location? So 3-dimensional or 4-dimensional, however you consider it. So you have the landscape, and you want to typically have the question, where am I, what is nearby, and how can I go there? And you would like to have this kind of 2- or 3-dimensional network. So you have a 3-dimensional or 2-dimensional map, and you want to ask, give me the closest restaurant to this point, or give me all restaurants within this area, or give me everything, what is the closest point to this restaurant, I don't know. So you have always this location related questions. And one solution to solve it, especially to find the one single node or that single peer which is closest to a specific geographical position, that's the question that we want to answer. So there are 2 questions basically. The one question is, what is the closest node to this specific point on the landscape, on the map? And the second question is, give me all of the nodes within one area, one specified area. The first solution that we look at is called Geodemlia, and it aims to provide this search for geographically close nodes. So give me the nodes that are closest to this single point on the map. So this is the goal. And what do you need for that? So first of all, you need a map, and you need some distances, and you need some metric system. So and what is given? You have a map with geographical positions, so a longitudinal and latitudinal description. So what is also used for GPS or whatever kind of maps you have. So you have this degrees and minutes and seconds as ID or as positions for the map. And every node has a geographical position composed out of these 2 values, has some IP contact and some random identifier. And also each object has some geographical position. It has a set of tags, okay, and a random identifier. And now what we want to do is to support these interfaces. So first, find the nodes in this which is closest to this position, and give me the k closest ones to this position. So you get the position, and you get how many closest nodes you want to have. For the Bloom filter, that we will cover, I think, in 2 lectures, what a Bloom filter is. But just to tell you, it is a short information about what you already know, so that you can tell in a short way, I know already these peers, so you don't have to tell me, just give me the others. But let's focus first for the first point. So give me all of the k nodes which are closest to this position. The second point, please store this object at that position. So link it to it, and if somebody makes a lookup for this position, then it should retrieve the object. And you can also create an area search. So this is the position, this is the radius, these are the search terms I'm looking for. And again, these nodes I know, so please don't tell me about them. So you both have the find the closest k nodes to a position and find objects in this area that I specify by position and radius, which have a specific set of terms. So like, I don't know, restaurant, Mensa, something like this. Okay, how does it look like? So it has some emlia in it, so it's somehow related to cardemlia, and this is how the routing table looks like. Okay, let's consider we have n predefined directions. It's easiest if you consider n equals 1. So, one moment, it should not be 0. Okay, yes, you have n predefined directions starting, so you calculate from 0 to n minus 1. It's easiest if you first imagine n equals 1, then it's almost cardemlia. So if you just take one specific, only this direction in the upper right corner, you have almost, exactly cardemlia. So you have one destination, you have the buckets, you have the distances, and for each distance, you have a k bucket of entries. Now, geodemlia introduces these directions so that you can split up your two-dimensional space around you in this n dimensions. As you see, this is a node-centric view. So this single node who is placed down here, this is his personal view on the network. So he created these directions, and because all of the nodes have this longitude and latitude information, he can identify if he learns about new nodes. So let's say he learns about some new nodes. One might be here, one might be there, one might be there. So just by messages passing by. And then he sees, okay, first of all, so let's say this new node is learned about. Okay, he is in this kind of direction. And out of my buckets, he is in this distance. So the distances are again very similar to the ones in cardemlia, just that not XOR is used, but again, so the closer you are, the more buckets, the more of these buckets you have, and the further you go away, the bigger the buckets get, so the more space they take. So you learn about a new peer, which can be placed in this kind of bucket, and then again you check whether you should place him in or not, and if you have space. If your bucket is not filled, you can put him in, and if there's no space, then you decide whether the last known one is still online or not. So what do we have to remember? So we can define how many directions we want to have. We calculate the directions starting with 0 to n minus 1. In each direction, we have this 160 buckets for distances as we had before. And every bucket has k entries again. And now, what is in this routing table? So, what is such an entry? So, about every peer, we know the position, the peer ID, and its contact, how we can communicate with him. And how is now the routing done? You might have seen this figure once again, so previously. So again, it does it exactly like cardemlia. So you have the parallel routing, you have the iterative routing, so you send out, let's say you want to communicate from this node, you want to find the closest spot around here. So what is the closest node around this single point? And then again you look into your bucket, this is this kind of bucket, and then you check out of your k entries which one is closest to this single position. Let's say we have k equals 2. Then this is one closest, and this one is not closest. So we contact these two alphamanic nodes we contact, and they reply with their closest personal views on the network. So it's really very similar. So they all have their personal view on the network, and they can give us more information about what they suggest, which k closest nodes to that specific position they know. And because it's iterative, then we get the replies back. And every node gives us k new nodes, and then we can again select the alpha best nodes out of these sets and contact them, and so we get, again, like in Kademlia, closer and closer. And as you also see, so let's say in the first place it was in our zero bucket, in our direction 0, so this one. For the second node that we contact, it's in this direction 1, so in this area. And so for every direction you maintain this kind of routing table. Then you do the routing, and now, as I said, yeah, that's almost, yeah, that's already it. And there's also this part of about the Bloom filters. I would like to tell you shortly about what the Bloom filters are and how they can be used to provide information in a very space-efficient way. So Bloom filters are, it's said, space-efficient probabilistic data structure that allows you to test whether an element is within a set or not. So let's say I have a very short, I have a Bloom filter. A Bloom filter might also be 160 bits. And I give it to you, and you can check very many, so a large number of elements, whether they are part of this set or not. And there are two answers. The one answer is no, and the other answer is maybe. So maybe might be a yes, might be a no. And this is quite useful because, so for example, we had here the task to tell, okay, please give me the k closest nodes around that position that you know, and I give you my Bloom filter, and if you check your k entries for my Bloom filter and you see it's not inside because there's the clear no, then give it to me. And if it's a maybe, then depending on whether you have better replies or not. So the no's are to be preferred. So you can always rely on this no. So this answer is guaranteed. And false negatives are not possible. On the other side, so the drawback is that maybe is a maybe. So it might be yes, it might be no, we don't know. But the whole Bloom filter is very space efficient. So this is the key. So even you can, so all of these objects have 160 bits. And you can still, if you have, I don't know, 20 elements or so, how else would you encode 20 elements, each with 160 bits, into one single 160 bits? So you have to really think about how you can most efficiently use it, and Bloom filters are very useful for that. So how do they work? So how Bloom filters work this way. So Bloom filter is an array of k bits. So it's always good to draw this. So an array of k bits. What does this mean? An array of k bits. Okay, so an array of k bits is a bit array with k entries. So it's no magic. So let's start with 0, 1, 2, until k minus 1. Okay. And each of these entries might be 0 or 1. Bit array. Okay, and what else do we have? We have m hash functions. So we have one hash function, we have an index, e, we can give some input, and this e can be from 0 to m minus 1. So you have m hash functions. And now what we do, if we get an object, so let's say we want to put an element into this Bloom filter. That means we want to modify the Bloom filter in a way that once somebody asks for that element, it will say maybe for the case that we look for the same object, and it does not say no. So what we do, we calculate the m hash functions and set all bits to 1. So this is always so we will get an example, but this is always the little bit tricky part. So what the hash function points at, what it has as an output is not 0 or 1, but it has an output from 0 to k minus 1. And let's say we are at the first hash function and it tells us 5, then we put a 1 in the Bloom filter at the position 5. And if the second hash function, so hash, the second hash function for the same object gives us the position 3, then we put at the position 3 a 1. So it always tells us which bits to set on 1 in the Bloom filter. And now once we check for membership, then again we take the same entry, so we have to know the key of the object, for example, and for all of these, so we get also the same indices in the Bloom filter, which should be 1. So if the object is inside, then all of these index must be 1. If one of it is 0, then we can say definitely this object is not inside. So let's have the example for this. So small example, we have two hash functions, so k equals 2. No, sorry, different. M equals 2. So m is the number of hash functions, and k was the size of the hash array, of the bit array. So k is 10. Yes, exactly. So in our case, so we have 10 possible places where we can set a 1, and we have 2 hash functions. So if we want to enter the element 0, it tells us for the first hash function 0, and for the second hash function also 0. So these are the places which we have to set to 1. So let's draw this somehow. So this is 0, 1, 2, 3, 4. So these are all the places, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have a bit array of 10 elements, and so the first element only gave us a 1 here, and all other elements are 0. Then we have a next element which is 1, and so we have to place it here in. So the first hash gives at the position 1 a marking, and at position 3 we also have to set 1. And now if you would search again for this same objects, so for example we would search for 1, then we see, okay, here is a 1, check, here's a 1, check, so it might be inside. And if we would search for the element, let's say 3 would give us also 3 and a 9. So it would have also here a check, but here we don't have a check, so we can definitely say 3 is not in the list. Okay, let's enter further elements. 4, that gives us 4 and 2, so here we have a 1, and here we have a 1, and 6, it gives us also here at 6 and at 8 a 1. So we could already try it. So this table now we have here. And now we can check for membership, 0, all. So if we put again 0 as an input for the hashes, and the indexes are 1 and 0 and 0, so we look up in the hash table in this Bloom filter the position 0 and there's a 1, so okay, it might be inside. For the element 1, we put it again in the hash functions, we get as index 1 and 3, we check the indexes 1 and 3 in the Bloom filter, they have 1s, okay, that might be inside. For 5, we see that at least one of the hash functions gives us a 0, so that means, so there is no marking at that spot where should be a marking, so we can say 5 is not inside. But we also have some false errors, like for example this 16, which is not in the Bloom filter. But if you apply it, then you apply the first hash function, 6 is the outcome, okay, check, we have a 1. And also here we have for 8, we have a check, so again, maybe. And while this is correct and this is correct, this is a false positive, and that's why it does not provide us information about a clear yes, it just tells us maybe. So only in the no we can be sure that if it's not inside, then one of the hashes will, one of the array bits will be 0. So this is quite useful because it allows us really to check the membership for O of M. Doesn't matter how large the objects are, we just have to consider how many hashes we use. Because the hash table, so it's like a hash table, the hash table allows us an access of O of 1, and because we have M times the hash functions, we have to repeat it M times. So it's a quick way to really have a look whether for memberships, it's independent of the hash size, and it's really, so you can also take very big hashes. It's a little bit more, so you still have to send it around. So if one had 60 bits as a Bloom filter is too small, you could also take larger ones. But it's really a very efficient and space preserving way to check for membership. There's also an extended version of it. It's called attenuated, so erweitertes Bloom-Filter of the depth D. And that means the following. Okay, so what does it mean? It means that if you are connected to other nodes, your Bloom filter of level 1 or of level 0 is only your own Bloom filter. The Bloom filter of level 1 is the union, die Vereinigungsmenge, of all of your first hop neighbors. The Bloom filter of level 2 is the union of your 2 hop neighbors. So how does this then look like? Let's make a new graph. So if we have the Bloom filter for only your elements, one moment, then it's, so this attenuated Bloom filter, so this is the level 1, level 0, this is only your elements that you have. And you might be connected to some other nodes. They also have their individual Bloom filters of level 0. They just check for their own data to create the Bloom filter for what they have. And if you create the union, so die Vereinigungsmenge, of all of these Bloom filters just by the OR operation, then you get the level 1 Bloom filter of this single node. And if you take the second level of hop, so of nodes also into account, so this, the contacts of your contacts, then you get the second level of Bloom filter. So why is this? Why does this make sense? This is sometimes useful if you are. So this is a general concept of the Bloom filters. If you are routing in some unstructured networks, then the nodes could use some Bloom filters to indicate in which direction it might make sense to route. So for example, if you know the Bloom filters of your neighboring nodes, you can decide in broadcasting or random walks or whatever, based on a better probability in which direction you might find the object. So you could directly leave those contacts out which don't have the match or the element indicated in several hops or so. So you just could follow those which have only a maybe. For this we will also have some exercise. Okay, so now we have this routing. And this is the Bloom filter. So what was the conclusion? So we have Kademlia routing in k dimensions, not in k dimensions, in d dimensions. Otherwise it's very similar. And now what does it also offer? So let's see how this storage and area search is done. So first of all, how do we find the position where an object might be stored, and how can we re-implement this area search around a specific position with a given radius? Yes, so it's the same way like the routing. So once you can route, you can also implement this kind of storage. So again, you have to go to the responsible peer in your surrounding, and once you find that peer, you will always find the closest peer to one specific position. And if you want to store the data, you just have to store it on that node. And if you do a search in a geographical area, then you can also contact first the responsible node for that specific circular middle point, and that node creates or tells you his contacts within this area that he knows. So that means, let's say you want to search in a radius around here, then of course you contact first the closest node to it, that might be this one, and this node tells you all of his contacts that he knows in this area, and all of the contacts you might also contact for that you are interested in something in this area, and they should just tell you for this specific area whether they have contacts. And the nodes can identify whether their contacts are within this area or not. And once you do this often enough, you have really for this whole area, you contacted all nodes, and they all could give you the information whether they have something fitting. And because this is very, you have to contact lots of nodes, that's why here the Bloom filters are used, so that you can make sure that you, with a high probability, only get new nodes that you didn't knew before. Okay. Yes. So how is the joining done, and how's the sort of the whole process, how to end it? So first of all, similar to Kademlia, so how do we join the network? We have to join somewhere, and then we find nodes at our own position. And once we know the nodes at our position, we can contact them. They can become part of our first routing table as the closest nodes. And by being part of the network, we get more and more nodes that we learn about, and our routing table is filled. So you first just have to know your own position in the network. How is the leaving done? Because you anyway have to consider failing nodes so that they just disappear, or nodes that might go offline and tell you before, so within a protocol, they anyway have to consider the case that they just leave the network, so they just can go offline, and this is detected as the same way it is detected in Kademlia. So once you want to put them into your buckets, so it's the same process again, you only throw nodes out of your bucket in two cases. Either you checked, so you wanted to use them, sent them a message, and they were offline, then you throw them out. Or if your bucket is full and a new node comes and you check the last seen node in this bucket and he's offline, then you also throw them away. So you don't really actively check whether they're online or not, just if you want to replace them in your routing table. Again, here you learn from bypassing messages, and the same bucket entry replacement strategy as Kademlia. So you want to prefer long-living nodes that are in your buckets, and you throw the offline nodes out. Okay, so very similar to Kademlia, just with the small twist that you have now this geographical routing by introducing these directions. Yes. So I would like then to stop the lecture here. So next week what you will see is further location-based overlays, and also what will come next week are heterogeneous structured overlays. So how can we introduce different questions? So what was heterogeneous again in P2P overlays? Yes, that's true, and that's true, yeah. So we have two concepts, so even here. So they are also hierarchical. So we have both nodes with different roles, and also we have layered overlays, where one overlay is on top of the other. So that we will have a look at. And also next week, I will be, on the one side, I think Tobias, no, not Tobias Amft, whom you already know, he will probably also present you one small part, but also Andreas Disterhöft, who is also a PhD student, he will also take the lecture because I'm not here. If there are any questions, send an email or contact me, but I hope it will be all okay. And you will also see, and that's really something to recommend, because now it's already set up, so next week it will be also a little bit tested. So we would like to ask you to also participate in a small peer-to-peer application to use it. that Andreas Disterf will present the lecture created, and it's really something nice, and it also shows you how code can be used in real life. It's very nice. So I would also like you to ask to use it and to test it and to give us feedback how well it works or where you find some bugs or something to improve. Okay, thank you very much, and see you then in 2 weeks from my side.